Now on this page, we'll revisit an example we saw a few pages back. In our discussion about the structure of confidence intervals, we said choosing a higher level of confidence means that we sacrifice some precision. This is only true if nothing else changes. But there is one way to keep a high level of confidence without sacrificing precision. We increase the sample size. We investigate the impact of a sample size on the confidence interval next. So going back to that cable strength example, recall that the engineers who are trying to determine the breaking weight of a cable, in that example, we had a random sample of 45 cables with a mean breaking weight of 768.2 pounds and a standard deviation of 15.1 pounds. From that sample, we computed a 95% confidence interval for the mean breaking weight of all such cables. Here are the important numbers we found from that calculation on the previous page. First, we found the standard error that was S over the square root of N. S was 15.1, which was given, and N was 45, so the square root of 45, if you divide those, you get 2.25. Okay, the critical T value, T sub C, we found using the applet, 2.015. The margin of error is those two numbers we found multiplied, the standard error times the critical T value. If you multiply those, you get about 4.53 if you round. Now the confidence interval we found was the 768.2, the sample mean, plus or minus that margin of error, which we just calculated above, was 4.53. If you add or subtract those, you get an interval from 763.67 to 772.73. Now let's increase the sample size and investigate the impact on the confidence interval. We calculate the confidence interval for a larger sample of 101 cables, mostly so that the degrees of freedom will be one less than that 100, a nice round number. The sample size affects our calculation in two ways. First, the sample size n appears in our formula for standard error. Also, the critical T value depends on the degrees of freedom. df, degrees of freedom equals n minus 1. So in this case, like we mentioned, degrees of freedom would be 101 minus 1, or 100, a nice round number. So we'll look at calculating the standard error first. S over the square root of n is 15.1 over the square root of 101. Using a calculator, you'd see that's 1.50 or thereabouts. Note that the standard error is smaller when the sample size is larger. We were expecting this because we know that there is less variability in sample means when the samples are larger, which we've mentioned before in a previous module. Finding the critical T value now. So to find the critical T value, we use the applet. We set degrees of freedom to 100, because like we said, degrees of freedom is n minus 1. So in this case, 101 minus 1. And the central probability to, we said we want 95% confidence, so it's 0.95. We see that the critical T value is 1.984 using the applet. Here's a picture of our work in the applet. Okay, now let's use this T value to do what we need to do. We'll just move down here. Okay, in the red writing here, note increasing the sample size decreases the critical T value. The T value went from 2.015 when n was 45 to 1.984 when n was 101. When we increase the sample size, you might also notice that both of the critical T values for 95% confidence are larger than the critical Z values for 95% confidence, which is approximately 1.96 from the previous work we did and further back units that we've done. This makes sense because the T models are wider than the standard normal curve, as we saw on the previous page, where different degrees of freedom give different curves, and we compared them to the standard normal curve, which was in the black dotted line, or black dotted curve, I should say. Find the margin of error. Okay, margin of error is T sub C multiplied by S over the square root of n. T sub C, we said using the applet, was 1.984 times the margin of error we found above, 1.50. If you multiply those, it's about 2.98. From there, we'll find the confidence interval. That should be X bar plus or minus the margin of error. And here's the margin of error. So we'll subtract that from the sample mean to get the leftmost number. We'll add it to get the rightmost number. So here are those numbers. 765.22 is the smaller number. 771.18 is the larger number. So in this table below, we'll look at the difference. The confidence intervals, how they change from the smaller sample size to the larger sample size. So notice with the smaller sample size, n equals 45, these were the values we got. The confidence interval went from 763.67 to 772.73. And then for the larger n equals 101, the interval was 765. This 0.222, that number is larger than the smaller number in the previous interval. And then all the way to 771.18, which is smaller than the one above it. So this interval is smaller. It's like the one for n equals 45 is a certain width, but if we looked at n equals 101, it was a narrower width. The interval is smaller, as we said. 101 is basically what they're trying to say here. So in other words, increasing the sample size had the following effects on the confidence interval estimate. It decreased the standard error. As we can see, we compared the calculations for n equals 45 and n equals 101 on the standard error. It also decreased the critical t-value. It decreased the margin of error and hence decreased the interval width. And it improved interval precision, as we see.